In this lecture, the main topics I'll cover are different types of non-radiative recombination mechanisms. Namely, I'll discuss in somewhat detail recombination generation through defects which give energy levels in the band gap. This is known as Shockley-Reed-Hall statistics. And then I'll go into brief description of Auger processes and then surface processes. Surface recombination. Recombination through defects is important because not only is it important in relevant in optoelectronics, but it's very important in all devices with junctions such as transistors, diodes, Schottky barriers, and one of the reasons why real diodes or transistors are different from idealized devices is due to the presence of recombination generation through traps or recombination centers. Broadly speaking, if you have a semiconductor which is characterized by a band gap Eg, if it's an ideal semiconductor, there are no states in the band gap. However, sometimes we put in intentionally shallow levels which are donors, and in other semiconductors we can put in levels, shallow levels, which are acceptors. And notice here that the definition of a donor is that it's a level with ED, which is usually much less than KT at room temperature. A donor, when it's occupied by an electron, the charge is 0. When it's empty, the charge is positive. So normally a donor is empty because electrons are excited into the conduction band. Similarly, an acceptor, the acceptor level EA should be less than KT. When it is occupied by an electron, it is negatively charged. Okay. And in that case, electrons are excited, so there are holes in the valence band. When it is not occupied by electrons, okay, it is neutral. Right? Now, in this picture, if there are additional levels which are towards the middle of the band gap, lower than what are known as demarcation levels, EDN, and here we have EAP. If we have levels there, for example, this can act as an electron trap if most of the time it is occupied by an electron. So, what is the definition of an electron trap? The definition of an electron trap is that unlike a donor, well, one can say that the energy Etn should be much greater than kT. Okay, and it is mostly occupied. That means the occupation probability is high at 300 K. And to further distinguish this as an electron trap and not a recombination center, we say that the emission probability from the trap is much larger than the probability of capture of a hole. Right? So, further, the electron emission probability is greater than that of hole capture. So one can write the rates. The electron emission probability will be given by, say, the number of electrons in the trap, okay, e to the power minus Etn by kT, and this should be larger than the hole capture, which is sigma p NTn into VTH. Or in other words, for an electron trap, one should have the condition that generally sigma n should be much larger than sigma p. The electron trap is in communication with mainly the conduction band. Okay? For a hole trap, the conditions are just the reverse, and sigma p should be much greater than sigma n. Typically, a hole trap will be, say, there, and it will be in communication with holes will be trapped and ejected. Now, in this picture, what are recombination centers? Recombination centers are centers typically in the middle of the band gap, through which electrons and holes can both be attracted and trapped. So the definition of a recombination center as opposed to a trap is that sigma n and sigma p should be comparable. Means one can be, say, 5 times or 10 times that, but that means this recombination center, once it captures an electron, and an electron is there, it has a finite probability for capturing a hole, and then it becomes neutral, right? Whereas a trap will capture an electron, and before it can capture a hole, the electron will be emitted out. Okay, so these are basic definitions of recombination centers and traps. Now, in a very good semiconductor, obviously, silicon concentration of recombination centers is extremely low. Concentration of unknown traps is also very low. You have only intentional donors and acceptors. But if you have a polycrystalline material, or if you have a thin film material, there will be appreciable recombination centers and as well as traps. the traps will lower the mobility. Recombination center will result in increase of dark current for solar cells or for transistors. The reverse bias current will increase due to recombination centers. And if you look at the IV characteristic of for PN junction, we know that this is given by e to the power QV over NKT minus 1. N is equal to 1 for an ideal semiconductor. And it can be shown that N is equal to 2 if you have these recombination generation centers. So the current in this case, log I against V, does not increase like that. It increases rather more slowly. This is the ideal region, N is equal to 1, and this is the recombination center where N is equal to 2. Okay. So this recombination generation process at low voltages is due to electrons and holes annihilating themselves in traps, and as a result, this current is much larger than the ideal current. Right. So let us now take a look at how recombination takes place through a single recombination center. For simplicity, we'll call this a trap, but it's understood that it is a recombination center in which both electrons and holes are recombining. Suppose the concentration of traps is NT at an energy ET. There are N electrons in the conduction band, P holes in the valence band, and this trap has trapped small nt electrons. Okay. So the fraction of traps occupied by electrons, Ft, is just Nt by capital Nt. We are looking at the SRH model, and from this treatment we hope to calculate what is the lifetime of carriers in this material with a single recombination center somewhere near the middle of the band gap, and what happens if the Fermi level in the material varies through the band gap. When it's highly n-type, the Fermi level is here. When it's highly p-type, the Fermi level is here. And as the Fermi level is moved through the band gap, how the lifetime varies. Okay. So we want to look at the behavior of this recombination center as it is capturing electrons and releasing electrons. And in thermal equilibrium, the capture rate must be equal to the release rate. So we look at the capture rate, which is, say, RC. The capture rate depends upon the number of traps that are empty, that is NT minus, capital NT minus NT, into the number of electrons here, which can be captured, that is N, and thermal velocity VTH into sigma N, the capture cross-section for electrons, which is a characteristic of this particular trap. So this can be rewritten as RC is equal to 1 minus NT by NT N NVTH sigma n. This is 1 minus ft into n into Cn, where we define Cn is ntv sigma n, which is the capture rate of per electron if all the traps are empty. And notice this is a property of the trap. It is the concentration of traps into the capture cross section. Okay, so that is the rate of capture. What is the rate of emission? We can say that emission rate will obviously depend upon the concentration of electrons in the traps. So the emission rate RE will be, say, we call that Cn dashed into Ft. And in thermal equilibrium, RE is equal to RC. So we have Cn dashed Ft is equal to 1 minus Ft n Cn. So this defines Cn dashed is just Cn n 1 minus Ft by Ft. What we mean by equilibrium is when there is no additional source like light or bias, which is creating extra carriers, which is adding to N and P. Now, if we talk about equilibrium values, then we can say that without any additional stimulation, we can say that N is equal to N0, and the distribution functions are Ft0, 1 minus Ft0, probability, this is state is empty, and this is the probability that state is full. So what is Ft0? These are for electrons, so this is nothing other than the occupation probability given by the Fermi function, and this is exponential Et minus Ef by Kt as given by FD statistics. So from this we can easily obtain 1 minus Ft0 by Ft0 is just exponential Et minus Ef by Kt. Now we know what N is in a non-degenerate system, N or N0. N0 is just given by the density of states in the conduction band, Nc exponential Ef by Kt. So we have Cn dashed is equal to Cn. N0 is Nc exponential Ef by Kt, and 1 minus Ft0 by Ft0 is exponential Et minus Ef by Kt. So this cancels, and this is just Cn Nc exponential Et by kT. And we can denote this by N1. So Cn dashed is N1 Cn. This is just for simplicity, where we define N1 is Nc exponential Et by kT. So this has a physical significance. This is nothing but the concentration of electrons in C band when EF is at ET. Okay? Because compare with this, N0 is equal to N. This is the concentration in the conduction band. Okay, when for a particular Fermi level. Now, if EF is equal to ET, then this N0 will be equal to N1. So this is the definition of N1. Now, under non-equilibrium conditions, when there is departure from equilibrium, either due to incident light or when the generation rate is R, then the net trapping rate Rn for electrons is R capture minus R emission, and we have calculated the values of these. R capture is Cn n1 minus Ft, and for emission we have C dashed n and into Ft. Now, C dashed n is just n1 Cn, so this is equal to Cn n1 minus Ft minus, n1 Cn into Ft. And if you take Cn out common, Cn into n1 minus Ft minus n1 Ft. So this is the capture rate for electrons. Now, similarly, we can write the capture rate for holes. We replace all the n's by p's, and where electrons are occupied, the states will be empty for holes. So we replace 1 minus Ft by Ft, and this will be P1 corresponding to N1, and Ft will be given by 1 minus Ft. So this is just by symmetry, where P1 has the same definition. P1 is the concentration of holes in V band when EF coincides with ET. Okay. Now, for a constant generation rate under steady state conditions, constant generation rate R, we have R, and there can be no charge buildup. The semiconductor must remain neutral, so Rn must be equal to Rp, and so we equate the relations that we have already derived for Rn and Rp. We have, for example, light being shone on the semiconductor, excess electrons and holes are created. N0 goes to N0 plus delta N, P0 plus delta P. But then if the generation rate increases, the recombination rate also increases. And we have a new steady state, okay, with this condition, R is equal to Rn is equal to Rp. So for clarity, if I write out the expression in full, Rn is equal to Cn into N1 minus Ft minus N1 Ft is equal to Rp, which is Cp Pft minus P1 into 1 minus Ft. So from this, we can write the ratio of Cn by Cp as equal to Ftp minus P1 into 1 minus Ft over 1 minus Ft n minus N1 Ft. Or from this we can calculate what Ft is. We can find out what Ft is. The occupation probability Ft is equal to NCn plus P1 Cp over Cn into N plus N1 plus Cp into P plus P1. The denominator is quite symmetrical, and if we substitute this in the expression for R, we get one of the most important relations, in steady state, the recombination rate is equal to CnCp Pn minus Ni squared over N plus N1 Cn plus P plus P1 Cp. You may wonder where Ni squared is coming from, where we have written N1 into P1 as obviously Ni squared. So we can further simplify this by dividing through by CnCp. So we have R is equal to Pn minus Ni squared over N plus N1 into tau P0 plus P plus P1 into tau N0. So comparing these, we can define tau P0 is just 1 by Cp. Remember, Cp is the capture rate for holes, so this is the lifetime for holes, and tau N0 is 1 by Cn. And remember, Cp is Nt Vth sigma p, and this is equal to Nt Vth sigma n. So these are the definitions of lifetimes for holes and electrons in this material. And if we examine this final expression, which is the final defining expression that gives the rate, we can examine this a little carefully, and it shows that, for example, in equilibrium, suppose there is no extra source, then P into N is Ni squared, right? If P into N is Ni squared, then this obviously the rate, recombination rate, net recombination rate, which is the difference between the emission and the capture, is equal to 0, right? We have defined the net trapping rate here is RC minus RE. Okay, this is, and under steady state conditions, R is equal to Rn is equal to Rp. Okay, so if these two are equal, our capture and emission are equal in when there is no extra generation, then obviously R is equal to 0, right? When P is not equal to P0, it is something extra, P plus delta P, P0 plus delta P, then this numerator is something finite, and obviously there would be a net generation rate. So this is a very important expression giving the overall SRH rate of recombination through a trap. The trap being defined by Cp. There's a concentration Nt. It has a capture cross section for holes of sigma p, capture cross section for electrons sigma n, and it is located at a level which is Et below the conduction band. Okay. Here we have taken the energy reference 0 at the conduction band. Okay, so this is minus something Et. Okay, now if we take some special cases, in N-type material, N-type material, N0 is much greater than Ni. Okay, N0 is also much greater than P0, and N0 is also much greater than delta P. So in N-type material, we can write N under steady state generation. N is equal to N0 plus delta N, and P is equal to P0 plus delta P, with the proviso that delta N is equal to delta P. Now, if we substitute this in the original expression, we find that R is equal to N0 plus delta N into P0 plus delta P, which is equal to delta N minus Ni squared over, and we find that N0 plus N1 tau P0, but from the previous assumption, the next term is negligible. P0 and P1 are negligible, so that is all that remains. And if we further simplify this according to the assumptions, we find that this is equal to N0 plus P0 into delta P. Okay, N0 into P0 is equal to Ni squared. So that cancels, right? So you have the term N0 into delta P and P0 into delta N. And delta N and delta, So we have delta n is equal to delta p, so we have n0 plus p0 into delta. We are neglecting delta n into delta p. Okay? And the denominator is now we assume that n1 is much less than n0. Why? Because n1 is the concentration when the Fermi level is at the trap. The trap is fairly low in. The trap is somewhere here. Obviously, the n1 is the concentration in the conduction band with the Fermi level here, which is negligible compared with n0. So we have the condition if we neglect that, then we have and for an n-type semiconductor we've assumed that n0 is much greater than p0, so this is also negligible. So we have the simplified expression that is very often used, that for an n-type semiconductor, the minority carrier lifetime being tau p0, the recombination rate is just delta p by tau p0. Okay? Where tau p0 is 1 by Cp is 1 by Nt V thermal sigma p. Or if we want to calculate, if we want to rewrite this, we often can say that the excess minority carrier is the recombination rate into tau p0. Okay. So this is for n-type materials. Similarly, we can define that tau p0 is whole lifetime n-type semiconductor, and similarly we can say delta n in a p-type semiconductor, delta n, the minority carriers will be r into tau n0, where tau n0 is the electron lifetime in p-type semiconductor. We can take another case, large injection condition, strong injection condition. When P into n is much larger than Ni squared, and P is almost equal to n, and we can calculate what is the recombination rate in this case. Then obviously we have R is equal to P into n over n0 tau p0 plus p0, neglecting the n1s, and this is equal to pn n0, and so we can take that out. So and then we have an effective lifetime tau p0 plus tau n0. And if we say that the P is equal to P0 plus delta P. Large injection means delta P is much larger than P0. Okay, then this condition is R is equal to delta P over. So it is exactly the same relation as before. Here R is equal to delta P by tau P0, but for large injection condition, where both electrons and hole recombination has to take place, it is delta P over tau P0 plus. So this is an important expression for large injection condition. Okay, in general, if you want to see how the recombination rate varies, we have a general case. R is equal to again, simplifying the numerator. And so suppose we say that this is equal to delta P over, this is the excess carrier density, over some tau effective, where the tau effective is the rest of the term. Tau effective is N0 plus N1 tau P0 plus P0 plus P1 tau N0, this over N0 plus P0. So the interesting case is to see what happens to tau F if we plot tau F as the Fermi level moves from the valence band to the conduction band. Suppose this is the mid gap, okay, EI. Suppose the trap is located there in the upper half of the band gap. So ET is there. So EI, this is EC, this is EV. How does this expression vary? Now, if the material is strongly p-type, okay, then we have the condition that when the Fermi level is here, the material is strongly p-type, okay, and then in a p-type material we know that the minority carrier lifetime is just tau N0, okay, and in a strongly n-type material we know the minority carrier lifetime is tau P0. Okay, so these are the two extreme conditions, and in between we want to examine which of these terms, so we can write this as the first term N0 plus N1 over N0 plus P0 tau P0 plus P0 plus P1 over N0 plus P0 into tau N0. Okay. So in an extremely p-type material, okay, this term N0 is very small, okay, N0, N1, all these numerator here is very small, so this is negligible. So we have only this term remaining. So here we have the value, this varies and this varies as tau n0 p0 plus p1 over n0 plus p0. Remember, as the Fermi level is varying, here it's strongly p-type, so p0 is much larger than n0. Here it is the opposite. Okay. What about this other term, n0 plus n1? The other term behaves as follows. This is the plot of the first term, tau p0 into n0 plus n1 over n0 plus p0. Remember, this is a sum of two terms. Okay, so the denominators are the same. This is the minority carrier lifetime of holes in an extremely n-type material, and this is the case for minority carrier lifetime of electrons in an extremely p-type material. Okay, and obviously the two add up, and if we add up the two, then how does the effective lifetime vary? The effective lifetime varies as the sum of these two graphs. It varies like so. This shows that when we talk about minority carrier lifetimes being tau n0 in p-type material and tau p0 in n-type material, these are the extreme cases. In general, the Fermi level is somewhere in the band gap. It is not here, it is not there. So in general, the effective lifetime follows this curve. Okay. And obviously you can see that here, when EF is in the mid gap, okay, this is as EF is varying, okay, as EF is varying from here to here. When EF is in mid gap, tau F goes through a maximum. Why? Because typically for an intrinsic semiconductor, okay, N0 plus P0 is a minimum. When the Fermi level is somewhere near the middle, okay, then it's an intrinsic semiconductor when N0 plus P0 is a minimum. Okay. So in other words, the trap has few electrons and holes to capture. So the capture rate is small, and therefore the lifetime exhibits a maximum. This is the general case, but we can say that for Cn much greater than Cp, obviously electron capture is much easier than hole capture. Therefore, when EF is in the middle of the band gap, tau effective is limited by ability of traps to capture holes, and then tau is equal to tau P0 into N1 in the mid gap. So to sum up, Shockley Hall Reed statistics shows that the effective lifetime is determined by the properties of the trap. The trap properties are given by NT, ET, sigma N, and sigma P. In an extremely P-type semiconductor, the minority carrier lifetime is tau N0. In an extremely N-type semiconductor, the minority carrier lifetime is tau P0. And in between, when the Fermi level is varying, then the minority carrier lifetime goes through a maximum. As I've drawn it, ET is in the upper half, and so the maximum is as shown. If ET was in the lower half, the maximum could occur in a different region. And of course, it depends upon the relative magnitudes of sigma N and sigma P. Remember, sigma N and sigma P are the capture cross sections measured in units of centimeter squared. Typically, the values of sigma N, sigma P could vary from 10 to the power minus 12 to say minus 10 to the power minus 20 sigma squared. This being a large capture cross section and this being a small capture cross section. And in general, the lifetime is tau is equal to 1 by NT V thermal. Tau N is, so higher the capture cross section and higher NT, we have lower value of tau N.